is we're going to consider a special case now of the shift cipher. So let's consider what we're going to refer to help us understand how the shift cipher works and some of the vulnerabilities it has. We're going to consider a special case of it called the Caesar cipher. So this is just simply an example of a shift cipher. So consider a special case of the shift cipher. Shift cipher with B is equal to 26, and the key is always going to be 3. So this is commonly attributed to Julius Caesar. I've also included some evidence for this claim as well from old literature. So I thought I would read a passage for you for dramatic purpose because I have it right in front of me. So I must stress also that versions like the Caesar cipher have been used also historically in the past. For example, by Augustus, which has connections with Caesar, using the key k is equal to 1, shifting by 1 letter. This shifts by 3 letters. So let me read this passage for you. For dramatic purposes, I'll read it in this fashion. There are also letters of his to Cicero, as well to his intimates on private affairs, and in the latter, if he had anything confidential to say, he wrote it in cipher, that is, by so changing the order of the letters of the alphabet, that not a word could be made out. If anyone wishes to decipher these and get at their meaning, he must substitute the 4th letter of the alphabet, namely D, for A, and so with the others. So that's from Life of Julius Caesar 56. so there's also some other fun passages also that you can find involving Augustus that talk also about this idea, but remember, Augustus used a somewhat different approach. But again, like I said, there may have been other ciphers used during these time period as well. This is just one that Caesar liked using apparently for private communications. In the time period of Caesar, okay, literacy was really low, okay, compared to today. So even being able to hide your messages in this fashion is already quite a high guard from someone that's your average person. Likewise, even if they were literate, the question of if even they could read the word, if they would understand that it's actually a bunch of cipher text that they did that this person specifically did some things to. It doesn't necessarily mean that they're going to understand that. They'll just see it's a bunch of gibberish. But the point I'm getting at is that you have to have some perspective on the past. That's what I'm saying. Here the key is already fixed. So it means that if you knew someone is using a Caesar cipher, you know right away k is equal to 3, and you know exactly how to decrypt their messages, right? So that's a problem, right? But we'll talk more about that in a little bit. So now that you know what's actually fixed, we can actually save a lot of time when it comes to computing stuff. Instead, we could just use a lookup table. And this is helpful for human eyes. So here's our table. Notice that everywhere I have a letter, notice that like I mentioned in my passage here that I gave you, wherever I have an A, it's going to be D, B is going to be E, and so on. Notice it wraps around, and the last 3 symbols are going to be those naturally because the key is 3. So everything gets shifted over by 3. So I thought it would be, let's go through some examples applying the Caesar cipher using this table. So notice that the reason how I came up with this table is I would convert these over to the numbers. I add 3 to each of their values, modulo 26, and then I convert it back to the symbol. But I cut a step out of here because it's intuitive enough for those that are using the English text here to know what's 3 letters ahead in the English alphabet. Like 3 letters ahead of A is D. So let's consider some encryption here. So suppose we have Caesar was here. Suppose that this is our plain text. So if I want to encrypt this, all I do is I look at my lovely codes here, my lookup table. So I have C, C becomes F, A is D, E is H, S is V, A is D, R is U, W is Z, A, W, and then we have A is D, and then we have S again. S was V, right? We have V, then we have H. H is K. So remember H over here, it's K right here. So I'm just looking up on the plain text symbol side and getting the corresponding ciphertext symbol. Then we have E. E is H. R, U, and then we have H again. And there's our ciphertext for Caesar was here. So let's do another one. Let's carry out this again. Let's go with learn and have fun. Seems appropriate, right? Learn and have fun. So learn and have fun. L. L is O. E is H. A is D. R is U. N is, where's N? It's Q. Then we have and, D, Q, and then we have D is G. You see how if you did this many times, this would go a lot faster? H is K, A is D, V is Y, E is H, and then I have the last three. We got fun. I, U is X, and then I lastly have N. N is Q. Let's make sure I got it all in there. Yeah, I got it. Okay, good. I just wanted to make sure. So here's a couple of examples of encrypting using the Caesar cipher. So notice that by taking out the middle steps of computing, I could just simply use this code, this list of codes. And this is how very often, if you want to encrypt things using a simple cipher like this, you might make a table like this one. So let's do some examples of decrypting. So below are examples of decrypting. Ciphertext of a Caesar cipher. So let's go through some messages. Let's see what we get. So we got P, V, N, L, W, W, B. So let's go through symbol by symbol. It's use the Caesar cipher deciphering approach here. So I'm going to shift back all of them by 3. But fortunate for us, that just simply means we look in the column for the ciphertext and we look in the corresponding plaintext symbol column. So for example, capital P, where's capital P? Capital P is right here. That means I put a lowercase m, or it's M. So this becomes M. How about V? Look for V over here, that's S. We got N, where's capital N? It's over there. It says K. Then we have L. uppercase L is an I. Then we have, then what else? We got W, got two W's. They're both T's. Then lastly, we have B. Capital B is Y. And look, this secret message says Miss Kitty. Meow. Yeah, so that's Miss Kitty there. Let's do another example. How about if I give you VPLOH? So let's go through the same process again. So capital V is S. Capital P, let's look for capital P, it's right there. It says put M. L, that's I over there. O is L. And then we have H. H is E. So in this case, we get smile. So lovely stuff, right? We got smile. Now, so hopefully you get the idea of the Caesar cipher. So notice that because I fix what the key is, I can come up with a table like this. And because I can do that, notice that all it does is it tells me that everything's being shifted by value k. And for each k, there exists such a table like this for a fixed b. Now, that brings me to an important point. How secure is the shift cipher? So let's consider some cryptanalysis. So let me tie this all up in a bow for us. I don't have a whole lot to say here, but I really want you to suppose that Eve, the eavesdropper, obtains the ciphertext. And wanted to determine K. K used to compute it from the plain text. I want to crack this sucker. So if I want to figure out what the plain text is, notice that in the shift cipher, the game in town is if you can figure out K, you can get back the plain text. But there's a little bit of something about the keys. Do you remember in the definition of the shift cipher what the key space is? So recall that the key space is in fact equal to ZB. So these are just the integers 0 up to B minus 1 inclusive. So if B is 26, for example, this would just be 26 numbers, 0 through 25. So one can exhaust, meaning can exhaust all possible keys and this, what I mean by this is the type of attack we're talking about here, or strategy. I should use the word strategy here to be a bit more precise. To analyze using an exhaustive key search. So this is what this will be referred to as. So just trying all possible keys until you find one that makes sense. So there's only B possible values, right? There's only B many. So please remember that there's only B possible values, and B is a constant, right? So what do I mean by an exhaustive key search? So try D0, D1, D2. So that means applying the decryption function or decryption with each key potentially being 0, then 1, then 2, and so on until some plain text is obtained to make sense. Meaning that I want you to find some sort of sensible plain text. So you just imagine you just take the ciphertext, you apply the decryption with different values of k. So you just imagine you just apply k for each one of them, and you'll get each time a potential plain text for Eve. So Eve can look at each one of them and says, okay, well, which one makes most sense to me? If it's sensible, it sounds like an English sentence or something like that, it likely might be the original plain text that Alice sent to Bob before encrypting it. So the cryptanalyst would analyze these potential candidates and see if this is. So what I want you to do, so this is an exercise, what I would like you to do is go through to our example here with the Caesar cipher, but don't tell them that you use the Caesar cipher, just tell them that they use the shift cipher. Show them the encryption and decryption, walk through the steps just like in our example before with the shift cipher, but don't tell them that you use the Caesar cipher. And see if they try k is equal to 0, k is equal to 1, k is equal to 2, and then when they get to k is equal to 3, ask them if they found your message. So in that case, notice that it would be sitting always when you try D3, right? That's what would happen for the Caesar cipher. So naturally, that makes the Caesar cipher incredibly vulnerable to attacks like this. In fact, it's very easy to attack if you know exactly what the key is in the first place. But in the shift cipher, you imagine you decide upon the keys in advance, and then you ask the question, okay, well, I could just try all of them, right? Well, you just try all of them. There's some constant number of them. It's big old one many of them that exist. You just try them all. And I must stress, remember, B is a constant, right? And normally you wouldn't have this thing being too big. The point here is that the key space is small or constant. So it is easy to apply cryptographic attacks such as in this case, we use the exhaustive key search to determine the plain text. So even if you made B so big that it would take somebody like a human quite a while to figure it out, that still doesn't make it terribly secure. Because keep in mind that it tells you everything you need to know about the key being used to at the same time. Likewise, just because the key space is big doesn't mean that somebody just doesn't have a systematic way of figuring it out in the first place, right? So the shift cipher is not secure, at least by our conditions of what secure means. Because Eve can figure out what the key is with a fairly simple attack.